G'day viewers. In this segment I'm going to tell you about distance vector routing, one of the two main methods which you use to find routes. So we've talked about the notions of shortest paths and how you can use Dijkstra's algorithm to compute shortest paths if you have the topology all in front of you. What we're going to see now is how to compute these same shortest paths but in a distributed network setting, as we need to in the internet. And we're going to look at what's called the distance vector approach to do so. Well, distance vector is a fairly simple approach to computing routes. It was used fairly on in the internet, actually when it was called the ARPANET, and also in a protocol that you might have heard of called RIP. Distance vector is one of the two main approaches towards routing, the construction of routes, that is. If you want to impress someone, I guess you can tell them that, technically this is a distributed version of the Bellman-Ford algorithm. Maybe that won't impress them, who knows. The algorithm itself works fairly well, it's correct, but it does suffer from very slow convergence behavior after some kinds of link failures. And for that reason, the kind of algorithms which we use to compute routes in most real networks today are often link state algorithms, which we'll see in a little while. These algorithms are a little more involved in terms of the work they do, but result in better overall behavior. Okay, now here's one thing that I would like to stress, because I think it's very interesting for our routing protocols. We had looked at a centralized scheme where you run Dijkstra if you know the whole topology. That's not how networks work at all. Okay, now we need to compute routes in a distributed setting. What is a distributed setting? Well, I'm glad you asked. It's really very different than the centralized setting where we have the whole network in front of us. In fact, if you're a node in this setting, all you know is your neighbors and maybe the cost to reach your neighbors. So you just have local knowledge. You don't know the overall topology at all. In terms of finding out things and deciding things, you can only talk to your neighbors using messages. You can't send messages magically to faraway places. You can only gossip and exchange messages with your immediate neighbors. It's also the case that all nodes run the same algorithm concurrently. There's no special leader or boss or centralized place that's in control of it. Every node is equal, and yet amongst themselves somehow they all need to decide on compatible routes. And just to make things a little more challenging, nodes and links can fail and messages can be lost. Actually, so it's not just the links that can fail and messages that can be lost, but nodes themselves can go down and fail. And that's going to be a little tricky because you might have been talking to a node a while ago and now it's gone away, and yet we still want to be able to find correct routes. How do we do this? Well, distance vector is one approach, and here's how it works just in one slide, and then we'll go through an example. Now, in the distance vector algorithm, each node maintains a vector of distances, let me just underline that, as well as next hops, to all destinations. This is the distance vector, and that's the heart of the algorithm. What you're going to do is compute the best distance vector and keep that best distance vector over time. So you start by initializing your distance vector with 0 for yourself as a destination, because you're already there, congratulations, and infinity to everywhere else. You don't know anything else. And then with this algorithm, all you do, and this is a simple repeated step, is you exchange every node sends its distance vector, the one it currently has, to all of its other neighbors. You keep doing this. And then as you receive from your other neighbors their new distance vectors periodically, you update your own distance vector. And you update your own distance vector to choose the best path, and that's going to be since we're after shortest paths, the lowest distance to each destination that you've heard. When you correct, of course, by adding the cost of the link towards your neighbor that you've just gone across. That's the one extra link from the distance vector information they gave you. And you're going to pick the best route and then you'll use it for forwarding. Okay, that's the distance vector algorithm. It's a little bit of a mouthful if you're not used to these kinds of algorithms. So let's see an example of how it works in practice. So here's a simple network. I'm just going to look at this basic network with 4 nodes, A, B, C, and D. And just a few links here. You can see I put the costs on all of the different links. And every node in this network is going to run its own instance of the distance vector algorithm and keep its own distance vector and exchange messages with hosts. Here, with its neighbors, excuse me. Here is the view of just the distance vector that A has at the beginning of time. So A says, well, I can reach A with cost 0. Great, I'm already here. B, C, and D, they're the other nodes in the network. infinity, don't yet know how to get to them best. And you'll note here that A can only talk to nodes B and D directly, can't reach C directly. So what happens? Well, what's going to happen is that A is going to send its distance vector to the other nodes B and D. Now B and D and all other nodes are of course going to be sending their distance vectors to all of the other links. So A is going to be receiving two distance vectors, one from B and one from D. And I put them here in this table. The distance vector tells us information to all of the different destinations, A, B, C, and D. And we can see what B says. B can just reach B, and everything else is infinity, and D can just reach D, and everything else is infinity. Now A needs to choose the best entries after correcting for the local link costs. So for B, we really want to look at B plus 3, because 3 is the cost to go over the link from B to A. So here's B plus 3 in this column here. You can see that I've added 3. And for D, we really want to look at D plus 7, because that's the cost of going over the link. And we want to choose the lowest number here as we go across. So what do we have? Well, A actually, to A, that's the special case. We already had 0. For everyone else, so to B, what did we find? Here was the lowest. It's just cost 3 going directly via B. To C, we don't have any lowest cost. It's still at infinity. And to D, we have 7. So that's going to go over here. And then we can see here is the distance vector that A has learned after the first iteration. And it will have, in fact, found the best one-hop routes which are possible in this network. And all you can do with one hop is just reach B and D directly. So this is what A is going to do. A is really here learning the minimum of B plus 3 and D plus 7, as well as for a special case of reaching itself at cost 0, because it knows its own identity. Of course, this same process is going on not simply at node A, but everywhere else. So wow, this looks a little more complicated, but let's just imagine for a moment what's going on elsewhere. Now here, this table here shows us all of the distance vectors that B, C, and D exchange with their neighbors. We worked out what happened at A. I've just copied it over here. B is going to learn the minimum of A plus 3 as it comes in here, C plus 6 as we come in on the link on the right, and D plus 3 as we come in those things. And I've written that there. I could also tell you that C is going to be equal to the minimum of, let's see, C is connected to B over a link with cost 6 and to D over a link with cost 2. So that would be what you would want to use to compute the routes for C. So if we follow the same process, and you can check this, hopefully I've got all of the numbers right, then you can compute the one-hop best routes that B, C, and D learn. Well, this process doesn't end. Actually, it's quite complicated thinking, just trying to keep in your head what's going on in all of these nodes. So I've tried to write it down. In the second exchange, here are the distance vectors that are going to be advertised. These are simply the best ones which were learned at the end of the first exchange. So they're going to be sent out. And we will then, every node will go through exactly the same process. And here you'll end up finding the best 2-hop routes after the second exchange. Well, what's A going to learn? Remember we said that A is equal to the minimum of what? B plus 3 and D plus 7. Well, let's look here. So we really want these ones plus 3 and these ones plus 7. What's going to be the minimum here? Well, to A, of course, is this special case of 0. To B, let's see. Well, 0 plus 3 is 3. That's lower than 10. So we're going to learn a route to, well, I guess we already had that. We're still at that. I've colored in pink here the ones that change. So what's actually changed? Down here, we've got C is, to C via B is cost 6 plus 3 is 9. To D, to C via D is cost 2 plus 7 is the cost of that link is also 9. So A now actually knows 2 routes to reach C at cost 9. So it will choose simply one of them. Let's say it's arbitrarily here chosen D, via D to reach C. Similarly, if we look down here, we have 3 and 3 is 6, and 7 and 0 is 7. So we find that A can actually reach D at cost 6 via B. It's learned a better 2-hop route. That is this route to get to D. We've now learned that that is shorter, cost 6, instead of this route that A was using after the first exchange. Well, this process continues. I'm going to leave you to check some of it at home. What we will find out is that we're now finding the best 3-hop routes, and there is actually some 3-hop routes that are better. A here is reaching C via B at cost 8. So that's actually going to be like this, is the shortest route. And it looks like we're actually using this in 2 directions. C is seen to A via D, so it's going to go like this too. So we found that as the best 3-hop route. Well, after that, if you go through and check all of this table, you should find that there are no shorter 4-hop routes because the diameter of this network is 3 hops. There are no longer paths. So we've converged now. And all subsequent exchanges should send the same information until there's a failure, that is, and then the routes may change. So in distance vector, you should imagine that in the dynamics here, in terms of adding routes, news about new possible routes is being added in 1 hop per exchange. Every exchange we were finding information about routes which were 1 hop longer. We haven't yet got to when you remove routes, but I'll tell you when you remove routes, what happens is that a node fails. So actually, it doesn't send a message saying, oh, you can no longer use any of my routes. What happens instead is that other nodes need to forget and time out the information over time if it's not reiterated. There are problems, though, with distance vector. Remember we said some convergence issues can arise, particularly with something that's called partitions. A partition is when you divide a network into 2 different portions so that you can't get from one side to the other side. If this happens because, say, a key link breaks, this is why you'll actually want more than 1 key link in network, so there's a little bit of reliability, you get a convergence problem. You get what's called the count to infinity scenario. Here's that scenario. So I've shown on the left the desired behavior. This is a simple chain, and we're looking at how information from the destination A propagates. You can see here good news, reaching A. News travels quickly. After 1 hop, B knows you can reach A at node 1. That's down here. After 2 hops, C knows you can reach A at cost 2, and similarly as we're going down and down and down this table. What about when there's a failure here on the right-hand side, and A can no longer tell people how it can be reached? Well, initially we'd found out all of these good routes, and now there's a failure. What's going to happen? Something strange can happen, actually. If you look at B, B will now get an announcement, not from A, because A can no longer reach it, but from C. C will say, well, I can reach A at cost 2, because that's what it could. So B will now say, okay, well, I can reach A at cost 3, because that is the C's distance plus 1 to go over that link. Well, you can imagine what might happen here. In the next iteration, C is learning how to get to A from B. C is going to raise its cost to 4. That will cause B to raise its cost to 5 and D to raise its cost to 5 in the next round. And subsequently, C is going to have to raise its cost to 6, all because they depend on one another. And you can see that something really screwy is going on here. This is called a count to infinity scenario because the network is really exploring ever longer routes in a vain attempt to try and reach a destination which is not reachable. And this is undesirable convergence behavior because it means that for a long time the routes in the network can be in flux. Now, you might think that my example was a little contrived because C shouldn't be fooled so easily. C knew that it was getting to, B shouldn't be fooled so easily because B knew that it was normally getting to A directly and it was in fact telling C the best route to use. So B shouldn't really decide to go via C and then just add 1 to the cost. It seems a little silly. However, these same effects arise in larger cycles, in longer paths in other networks, even when you're not talking to one another directly. Cycles of 3 nodes and so forth. So they're very involved in these networks and they're quite hard to get rid of. There are various heuristics. They have colorful names here like split horizon and poison reverse. Just means, B, don't suddenly start using information from C if you told C how to actually get to A. But these heuristics turn out not to be very effective in practice. They get complicated and they don't really solve the problem in nearly all of the cases. For that reason, link state algorithms are more favored in practice. And we'll look at link state protocols in the next segment. One exception is that distance vector is really very lightweight. All you're doing is keeping this distance vector and propagating it. No complicated graph algorithm. So you can use distance vector when you're very resource constrained, might be one exception. Okay, so distance vector is the technique. Distance vector is the technique which is used in a protocol called RIP. You might have heard of it. It's one of the more famous distance vector protocols. So it uses hop count as a metric. So we're simply counting the number of hops routers we go through, and we use infinity as 16 hops. Just to this limits the network size, but also stops us exploring ever longer routes in case of some of these weird things. It also includes these heuristics for split horizon and poison reverse. RIP is actually quite an old protocol now. You're unlikely to use it in practice. So you might look at it just to understand how some of these protocols worked. There's an old RFC you could look at. It's it's quite dated now, but it's a nice small RFC. You can read the whole thing and understand the protocol. You'll get all of the details like the 30-second timers for sending these distance vectors. It's run on top of UDP. Information times out if a node goes away after 180 seconds as a way of detecting failure. So there can be a failure. Once there's a failure, it can be a long time before the network responds and fixes routes. This is not so good these days. And this is why we run faster and better routing protocols these days. But nonetheless, it's an interesting protocol to look at. Okay, you know about distance vector.